In this video, we're going to solve the same circuit again. This time we're going to apply Thevenin's theorem in order to solve it. Now, that might not even be very efficient, but it's just a way to show you that Thevenin's theorem also works with the phasor notation here. Now we have to decide exactly how we want to apply it. Since we're looking for the current through this resistor, I'm going to take everything else and find its Thevenin equivalent to simplify it down. So I'm going to treat that as my load resistor. So we'll go ahead and first find my VOC, my open circuit voltage. So I'll start by combining the ones that are in series, 1 plus J impedance here. I've got my current source. I've got my second voltage source, first voltage source, second source overall. I've got my open because I'm doing VOC here. And then I have my 1 minus J over here. Now VOC is this voltage across these terminals, which is also the same as just my V2 up here. So just realize that V2 is what we're looking for. I'll probably go ahead, mesh current, there's two meshes. Node voltage, there's two nodes, but you have to do a super node. However, I can even make it easier by just using source transformation here, combining this current source and impedance and making it into a voltage source with an impedance in series. So 1 plus J times 2 is 2 plus 2J. We have our 1 plus J here. We have our 6 volt source, our opening, and then finally 1 minus J over here. And then I can combine those two sources together. 6 plus 2 plus 2J is 8 plus 2J. Then we have 1 plus J over here, 1 minus J. And we have our VOC of these nodes. Now at this point, since the open nodes for VOC is in parallel to the 1 minus J, I can just use a voltage divider here. So VOC is the total voltage times the impedance you're at over the sum of the impedances. And so if we go ahead and multiply this out here, I'm going to have 8 plus 2J times 1 minus J. And the denominator is just going to be 2 there. I'm going to get 5 minus 3J is my VOC. Then I need my R Thevenin. So for my R Thevenin, since everything is an independent source, I can make my life easier and just combine everything together. Inductors become opens. Voltage source, sorry, not inductors. Current source become open. Voltage source becomes a short. I'm finding things from respect to that. And we have 1 and minus J. So we're trying to find our R Thevenin from these two nodes here. So it looks like my 1 plus J and 1 minus J are in parallel. So R Thevenin is 1 plus J in parallel with 1 minus J, which we did on a previous video. Turns out to be just 1 ohm. So that's my R Thevenin. So my Thevenin equivalent circuit becomes a voltage source that is 5 minus 3J with my R Thevenin of 1 ohm. Now I'm trying to find the current when you put a load resistor in here that is 1 ohm. And we can go ahead and find that by just doing Ohm's law here. It's the voltage divided by the total resistance. It's going to be 2.5 minus 1.5 J. And then we can quickly do the same thing we did before. Convert that into polar. Get the 2.92 angle negative 31.0. That means my I0 of t, same thing we got before, 2.92 cosine omega t minus 31.0 in terms of amps. So So again, it's about the same amount of work as some of the other ones. The main point of this video, though, is to show you that Thevenin's theorem, along with everything else we've been doing, all works with phasor notation.